Okay, so we have two curves, 3/4 sin x and y equals tan x plus a fifth. So using the exponential versions of those and equating them, we get 3/4 and then the hyperbolic sine e to the x minus e to the minus x over 2. That's going to be equal to hyperbolic tan e to the x minus e to the minus x all over e to the x plus e to the minus x plus 1/5. To tidy this up, first thing I'm going to do is try and get rid of the fractions. So I've multiplied everything by 40, and that should do enough cancelling. So we've got the 3/4 and the half on the left-hand side becomes 15. Then we've got 40 lots of the hyperbolic tan, and then 1/5 becomes 8. Next step, multiply by e to the x plus e to the minus x to eradicate fractions completely. So we've got 15 lots of e to the x minus e to the minus x times by e to the x plus e to the minus x. That's going to be equal to 40 lots of e to the x minus e to the minus x plus 8 lots of e to the x plus e to the minus x. Start expanding things out now. On the left-hand side, it's a difference of 2 squares almost. We end up with e to the 2x minus e to the minus 2x, and then expanding the right-hand side and collecting them together. 40 e to the x plus 8 e to the x is 48 e to the x, and minus 40 e to the minus x plus 8 e to the minus x is going to be minus 32 e to the minus x. Expanding out the left-hand side, 15 e to the 2x minus 15 e to the minus 2x. I'll leave the right-hand side alone. Then I'm going to multiply everything by e to the 2x. So it becomes 15 e to the 4x minus 15. It's going to be equal to 48 e to the 3x. Subtract 32 e to the x. And lastly, bring everything onto the left-hand side. And we get the equation we wanted. For part B, I've decided to factorize e to the x minus 3 out of the disguised quartic. So we get e to the x minus 3 lots of 15 e to the 3x, subtract 3e to the 2x, subtract 9 e to the x plus 5, and that's equal to 0. Therefore, e to the x equals 3 is a solution. For part C, well, if e to the x equals 3 is a solution, then x will be equal to natural log of 3, x equals ln 3. And we can plug ln 3 into our expression for hyperbolic tan of x plus 1/5. So we get e to the x is 3, e to the minus x therefore is a third. 3 minus a third over 3 plus a third plus a fifth is 1. So our point P is a point natural log of 3, 1. For part 2, we're asked to integrate. So we're integrating between -4 and 0, e to the 1 over x squared. I'm going to use a substitution here, u equals 1 over x. differentiate that, we get minus 1 over x squared. And therefore dx is equal to minus x squared du, if you forgive me for splitting the variables like that. If you've not done it that way, that's absolutely fine. You've done it the proper way, but I know that you guys quite like coming up with a substitution for dx in terms of du. So there you go. Carrying out the substitution, we get e to the u over x squared times by negative x squared. The x squareds will cancel, so we're integrating minus e to the u du, which integrates to minus e to the u. Reversing the substitution, I'm going to reverse it in a way that sets a parameter t instead of 0, because if we plug 0 in, we'd be doing 1 divided by 0 in the calculation. So I'm going to put t in as a parameter, and I'm going to let t tend to 0. So plugging t in, the limit of t tending to 0 of minus e to the 1 over t. We're coming in here from the negative side, so t is tending to 0 when it's negative, so we're going to get e to the power of a very large negative number, which is going to tend to 0 as that happens. So the limit as t tends to 0 from the negative side of minus e to the 1 over t will be 0. Plugging negative 4 in is straightforward, just minus e to the minus a quarter. So we get 0 subtract negative e to the negative a quarter, which is e to the negative a quarter, which is what the question wanted.